Ever wondered how to traverse every edge of a graph exactly once without lifting your pencil? Let's delve into the fascinating world of Eulerian trails and circuits. Named after the Swiss mathematician Leonhard Euler, these mathematical concepts allow us to explore the intricacies of graphs in a unique way. An Eulerian trail, you see, is a journey through a graph that takes you over every edge precisely once. Imagine walking through a park, crossing every bridge only once, and you've got the idea. Then, there's the Eulerian circuit. This is a special type of Eulerian trail that starts and ends at the same vertex. It's like taking a leisurely stroll around your neighborhood, making sure to traverse each street only once and ending up back at your own front door. Now that we have a basic understanding of Eulerian trails and circuits, let's explore the conditions for a graph to possess them. An Eulerian trail isn't present in every graph, so what are the conditions for a graph to have one? Let's dive in. Firstly, we need to understand that a graph is a collection of points, known as vertices, and the lines connecting these points called edges. An Eulerian trail is a route in a graph which visits every edge exactly once. Sounds simple, right? Well, there are certain conditions that a graph must meet in order to have an Eulerian trail. The first condition is that the graph must be connected. This means there should be a path between every pair of vertices. In other words, you can get from any point to any other point without having to jump off the graph. The second condition relates to the degree of the vertices, which is the number of edges connected to each vertex. For a graph to have an Eulerian trail, it can either have exactly two vertices of odd degree, or all vertices can have even degree. But what does this mean exactly? Well, a vertex has an odd degree if the number of edges connected to it is an odd number, and an even degree if the number of edges is an even number. So, if all vertices have an even degree, you can start at any vertex, follow the trail, and end up back at your starting point, having visited each edge once. Alternatively, if there are exactly two vertices of odd degree, you start at one of them, follow the trail, and end up at the other, again visiting each edge once. Let's consider a simple example. Imagine a graph with four vertices, A, B, C, and D. Vertices A and D each have three edges, making them of odd degree, while B and C each have two edges, hence of even degree. This graph satisfies the conditions for having an Eulerian trail. Easy, right? Now let's move on to the conditions for a graph to have an Eulerian circuit. What about Eulerian circuits? Can any graph have them, or are there specific conditions? Let's find out. First and foremost, let's refresh our memories on what an Eulerian circuit is, shall we? An Eulerian circuit is a closed trail in a graph that visits every edge exactly once. In simpler terms, it's a tour around the town where you cross every bridge once and end up back at your own doorstep, without retracing any steps. But can any graph have an Eulerian circuit? Not exactly. There are indeed special conditions that a graph needs to meet. The first condition is that the graph must be connected. This means that there must be a path between every pair of vertices, no isolated islands here. The second condition is that each vertex in the graph must have an even degree. The degree of a vertex is the number of edges connected to it. This condition is essential because, for you to leave a vertex by a new edge, you must first arrive at it by a different edge. If every vertex has an even degree, you can keep moving along the edges without getting stuck. Let's illustrate this with an example. Imagine a graph with four vertices, each connected to the others, forming a square. Each vertex has a degree of 2, which is an even number. Additionally, the graph is connected, as there's a path between every pair of vertices. Therefore, this graph has an Eulerian circuit. You can start at any vertex, travel along each edge once, and return to your starting point, having fulfilled your Eulerian duty. But what if we add one more edge connecting two vertices? Now, two vertices have a degree of 3, an odd number. Can you see the problem? You might end up at a vertex with no way to leave without retracing an edge, meaning no Eulerian circuit is possible. Now that we've covered the conditions for a graph to have Eulerian trails and circuits, let's summarize the key points. We've learned a lot about Eulerian trails and circuits, haven't we? Let's quickly recap. Eulerian trails and circuits are all about traveling through a network, visiting each edge exactly once. An Eulerian trail allows you to start and finish at different vertices, while an Eulerian circuit demands you start and finish at the same vertex. To have an Eulerian trail, a graph should have exactly two vertices of odd degree, or all vertices of even degree. For an Eulerian circuit, all vertices must have an even degree. For example, let's consider a graph representing a city, where the vertices are destinations, and the edges are roads connecting them. If each destination has an even number of roads leading in and out, a postman could start at any point, deliver mail along each road once, and end up where he started, without retracing his steps. An Eulerian circuit. Now let's talk applications. These concepts are not just intriguing mathematical puzzles, but practical tools that can help solve real-world problems. For instance, in waste management, garbage collectors need to cover all streets in a city without doubling back, saving time and fuel. This is an Eulerian circuit problem. If the city's road network meets the conditions for an Eulerian circuit, they can start and finish their route at the depot, traversing each street once. Postmen too benefit from Eulerian trails. Their route could start at the post office, cover all the streets once, and end at a different location, where they can easily return to the post office. And in the realm of genetics, Eulerian paths are used in DNA sequencing. Scientists construct graphs where vertices represent different DNA fragments and edges represent overlaps between them. An Eulerian path